Due to the strong temporal and spectral mode confinement, the threshold power of the parametric oscillation via the current nonlinearity is significantly reduced to sub-milliwatt level. Then degenerate and non-degenerate for mixing occurs and generate new frequency sideband on other resonance. So as a result, the output spectrum through the resonance constant of equidistant grid of lines. So the accurate frequency of each comb line can be described by this formula. An important achievement in recent years is the demonstration of dissipative Kerr solitone, that is, the microcomb state with high coherent and low phase noise. Analytically, the system can be described by this Loggiato-Lefevre equation. So under the special conditions such that the cavity dispersion balances the nonlinearity and the gain balance the loss. So there will be a solution from the equation that is the traveling pulse with the CW background. And this solution is called the solitone. And this will provide the microcomb spectrum with smooth square profile. So this slide lists the three mostly used material platform for integrated photonics. So they are silicon on insulator, silicon nitride, and indium phosphide. So among them, silicon nitride features several advantages, which makes it ideal platform for microcomb generation. For example, it have a large band gap of 5 electron volts, so which means that the two photon absorption is negligible at the communication wavelengths. And also it is wide transparent from the visible to infrared, and also it has high power handling capability. And the dispersion of the silicon waveguide can be controlled by changing its cross-section geometry to meet the requirements of microcomb generation. So our lab has developed a novel silicon nitride fabrication technique called the photonics damascene process, which is inspired by the damascene process for fabricating Cooper interconnectors. So different from the subtractive process, the waveguide and stress release filler pattern are right directly on the silicon oxide substrate via the deep UV step lithography. The use of the DUV in contrast to the commonly employed electron beam lithography enables a dramatic increase in fabrication throughput, stability, and reproducibility. So this is essential to large volume manufacturing. So all the fabrication processes are carried out in EPFL Center of Micro Nanotechnology. So the use of using this fabrication technique, we have successfully fabricated silicon nitride microresonators with FSR from 2 GHz to 1 THz, and silicon nitride waveguides with several meters long. So another key figure of this fabrication technique is that the yield is very high. So we can obtain more than 116 usable chips per wafer. So each chip contains several micro rings can be used. So the fabrication lead time is within 1 month. Then we characterize the silicon nitride microring fabricated by above-mentioned photonics damascene process. The statistic study of this microresonator quality factor is shown in this figure for both fundamental TE and TM mode. More than 10,000 resonances are measured covering the whole wafer, so the most probable value for intrinsic line width is 6.5 MHz, corresponding to a quality factor more than 30 million. This means that the linear propagation loss is around 1 dB per meter for physical length and 0.5 dB per meter for optical length. So during a quite a long time, it has been a standing challenge for the integrated photonics community and the microcom community to obtain 10 or 20 GHz integrated solitones. This is because it's difficult to achieve high quality factor in such a large ring. So thanks for our photonics damascene process, which we can obtain sub-nanometer level surface roughness for centimeter long waveguide, so that now we can generate a solitone microcomb with such low representation rate. So this slide shows the microwave representation rate solitones that we obtain from our silicon nitride microresonator with FS of 10 and 20 GHz. The threshold power for a single solitone generation is around 15 milliwatts for 10 GHz solitone and 40 milliwatts for the 20 GHz case. The 3BD bandwidth for 20 GHz solitone is around 27 nanometer with more than 170 comb lines. For 10 GHz solitone, the 3 dB bandwidth is around 26 nanometer with common lines more than 300. So the right photo shows a typical packaged 10 GHz silicon nitride chip on submount. So the direct application of microwave repetition rate soliton is that we can get the microwave signal by simply detecting the soliton pulse with a high-speed PD, as shown in this schematic. So this figure shows the single sideband phase noise of the detected soliton pumped with either the Toptica diode laser or coherent fiber laser. So with coherent fiber laser, the 20 GHz soliton-based microwave carrier exhibits low phase noise with the parameter list here. So in order to have a better understanding of where the soliton phase noise comes from and how to further reduce the soliton phase noise, in the following slides, we are going to analyze the soliton phase noise performance in detail. So first, we investigate the laser phase noise to soliton phase noise transduction. Since the Toptica laser has a typical fixture around 3 kilohertz, and by comparing this feature in both laser phase noise and soliton phase noise, a minus 15.5 dB from octo to microwave phase transduction is determined, and we should write from the conversion of the detuning fluctuation to repetition rate fluctuation. So by operate the laser detuning at the so-called quiet point, so this transduction value can be even lower due to the canceling between the Raman-induced soliton self-frequency shift and the dispersive wave recoil. So the details of the quiet point can be found in this paper. So the second, we investigate the laser relative intensity noise to soliton phase noise transduction. The measurement setup is shown here. So the pump power of the laser is modulated by an AOM with a certain frequency, which will create a calibration tone in the soliton phase noise spectrum, so that we can calculate the ring to soliton phase noise transduction at different frequency, as shown in this figure. So it follows a slope, and which can be described by this formula. So the conversion efficiency alpha is calculated to be 79 Hz per milliwatt. So previous slides show how the pump laser transfers its phase noise and relative intensity noise to the generated soliton phase noise. So in this slide, we will investigate which is the main phase noise limit caused by the laser. For the case of using coherent fiber laser as a pump, we plot both the laser phase noise and the ring after transduction together with the soliton phase noise. So the blue curve here is the soliton phase noise. So the red curve is the transducted laser phase noise, which is below this blue curve. And the green curve is the transducted laser ring, which shows similar profile with the blue curve from the 10 Hz to the 100 kHz. So this means that the coherent laser ring is the main contribution for the soliton phase noise in our case. So besides the noise introduced by the pumped laser, there is a fundamental noise limit from the microresonator itself. Here we would like to discuss the thermal reflective noise in silicon nitride microresonator. So this noise is caused by the thermodynamic fluctuation of temperature, which will result in the refractive index fluctuation, and further result in the resonance jittering and the soliton detuning. Even your laser now is very stable. So this figure, so our group has both measured and theoretically simulated the TRN in silicon nitride. Detail can be found in this paper. Since this TRN can influence the resonance detuning similar as the effect of the laser phase noise or laser jittering, so we can calculate the TRN effect on detuning by subtracting 15.5 dB from its original value, is shown as this red curve. So on the other hand, the TRN can also directly influence the soliton repetition rate due to the thermal-induced FSR fluctuations. So this effect can be calculated by simply multiplying the FSR and the mode number, so which is around minus 80 dB from the original value to yield this resonance TRN. So this is it is shown as a yellow curve, and which is the fundamental TRN limit. So now we can plot these TRN curves together with the soliton phase noise and the noise transduction of the fiber laser in one figure. So it can be seen that the soliton phase noise is not only limited by the laser ring, it's also limited by the TRN effect on detuning between the 1 kHz to 1 GHz, seen in this dashed black line. So this means that even we find a laser with lower ring or phase noise, the soliton phase noise cannot be reduced due to the TRN effect. So now we'll continue working on understanding the TRN effect on soliton phase noise, and we also have some idea to reduce this effect. For example, we can integrate the silicon nitride with other materials that have opposite thermal optical coefficient, which might can help compensate the TRN effect and reduce the soliton phase noise. So this figure summarizes the phase noise performance of the integrated oscillators reported before. Our silicon nitride soliton microwave signal is a black curve. So it is not bad and can be further improved to approach this fundamental limit. So here we show that the microcomb can be used for low noise microwave signal generation. Actually, it can do more for microwave photonics. So it can also be used as a compact multi-wavelength optical source. So the second part of this talk it will be about the microcomb-based microwave optical filter. So this figure from a review paper highlights very well the roadmap of integrated RF photonics filter. So there will be many ways to implement RF photonics filter, for example, using the narrow linewidth from a Boolean and or a resonance from a micro ring. So while some others are based on programmable multiprocess microwave photonics circuit like optical FPGA. So in this talk, we will focus more on the RF filters that are based on taped delay line structure with the help of the microcomb. So one of the approach of making an RF filter that based on the tape delay line structure is using the multi-wavelengths source together with the dispersive propagations. So here shows the concept, and it contains four parts. So first, the multi-wavelength source has to be generated, and second, the microwave signal is modulated on the multi-wavelength source. Third, the modulated comb are propagating through a dispersive element like a kilometer-long single-mode fibers. And finally, the optical signal is bit and received by a photodetector to retrieve the RF signal. So by working out the math, we can find that the response RF filter is given by the Fourier transfer of the multi-wavelength intensity profile. So typically, people use a bank of laser arrays or active Moloch lasers or EO combs generated from the cascaded modulators as the source for the IF filter, photonic filter. So the multi-wavelength source used here needs to satisfy some requirements. For example, the large laser line spacing is needed for the filter to have a large spur-free range. So we also appreciate a large number count of laser lines because it's basically the number of filter tape. And of course, we want the source to be smaller the better. So all this naturally come down to the integrated microcombs, which not only provide compact solutions, but also have a very large comb spacing and many comb lines at the filter tapes. So indeed, there have been several microcomb-based RF photonic filters that are demonstrated in the past, and they are based on some specific comb state like the dark pulse microcomb or the complex soliton crystal microcomb. So we know that for all these demonstrations, they required a two-pulse shaper in their setup. So the first pulse shaper is needed to smooth the microcomb spectrum in order to obtain the microwave filter signal with good expression ratio. So while the second one is needed for the filter tunability. So here, although the comb part now is integrated, but the use of the two pulse shaper clearly complex the setup. So on the other hand, the soliton state of microresonators are intrinsically well-shaped. So therefore, we can bypass the use of the first pulse shaper. For example, the spectrum of a single soliton state shows a very smooth such square shape. In addition, the microresonator can also provide multi-solitons it is found that the number of solitons inside the microresonator can be precisely controlled by backward tuning method. So for example, here it shows the spectrum of a two-soliton state, and the insert shows the relative soliton distribution. Here, the Sech-square soliton spectrum is being modulated by the sine wave induced by the spectral interference of these two solitons. And it is recently found out that a perfect soliton crystal can be obtained at low pump power. So perfect soliton crystals are equally spacing in one round trip. Here shows the four equally spaced solitons, and therefore the cone spacing is also enlarged by 4 times. And all these different soliton states will be used for the reconfiguration of IF photonics filters, so that we don't need the second pulse shaper. So here it shows the simplified experimental setup. The filter response is measured by this vector network analyzer. So when the soliton state is a single soliton state is used, the IF response can be described by this formula. So the G function is a line shape corresponds to the Fourier transfer of the Sech-square function, and the cosine term in the envelope fading is envelope fading induced by the dispersion. And here is negligible in our case thanks to the large microcomb spacing. So this is the experimental single soliton spectrum, and this is the corresponding IF filter response. So the filter passband is centered at around 60.2 GHz, which is determined by the length of single mode fiber and the microcomb spacing. So the smooth Sech square envelope of the single soliton guaranteeing the filter with good side mode separation ratio without the need of the external shaping. So in addition, the IF passband can also be reconfigured by the perfect soliton crystal. Here it shows the filter response in this case. And basically, the perfect soliton crystal multiplying the comb spacing, therefore it divided the center frequency of their IF filters. So in the experiment, we obtained 2, 3, 4 perfect soliton crystals by pumping different resonance on the low pump power. So the IF passband are then correspondingly divided by 2, 3, 4 times to 8.1, 5.4, and 4 gigahertz. All of the obtained IF filters here shows good separation ratio of more than 20 dB without external pulse shaping. So in another way, the IF filter can be reconfigured using the two-soliton state. So the IF filter response in this case is described here in this equation. So here the alpha is the relative angle between two solitons. And we can see that in addition to the original filter response, the new RF passband approach appears on both sides of the initial response. So with the displacement determined by the relatively soliton angles, so therefore the soliton filters can reconfigured by changing this angle. Uh, so we can see that so this shows the experimental obtained two soliton spectrums and their corresponding IF filters. So we can see that indeed the frequency of the new passband increased as the soliton relative angle increases. So it was to mention that all these two soliton spectrums are obtained from the same resonance. So it simplified the setup. And also, what happened here is actually linked to the avoid mode crossing, which induced the background modulation that lock the relative position of two solitons and also determine the IF filter response. So the performance of our filter is compared to other cone-based IF filters that are listed in this table. So compared to those using Moloch laser or Eucombs, microcomb indeed simplify the light source part. So compared with the IF filter of the same type that using microcombs, our implementation is much simpler since we bypass the use of the two-pulse shaper. So our filter is widely reconfigured, and also the side mode separation ratio is also good, and it can be further improved by using like the integrated pulse shaper. And also you can refer for this literature about all the IF photonic filter that I mentioned. So here come to the summary part of this talk. So in this talk, we discuss the application of integrated microcomb for microwave photonics. So two applications are presented. So one is using the solid microcomb to generate a low loss microwave signal. So this is enabled by our photonics damascene technique, which provide us high yield silicon nitride microresonators with ultra low loss that less than 1 dB per meter, corresponding to a quality factor more than 30 million. So in the 10 GHz and 20 GHz samples, we obtain solid microcombs with microwave K-band X-band repetition rate. The phase noise is also characterized, and also the noise source and the limit are also discussed.